Okay, so we're going to just start to talk about acids and bases. I'm going to be combining equilibrium, which is really like a one-day chapter. It's really small. You can watch the video. It's a little bit longer, but it will give you all the information you need to know. We're going to combine that with acid bases, and this is just because it's going to make life for the HL students a lot easier. So there's a lot of ideas that go together in these two units, and I'm going to use that to help speed us up so that we can get through the rest of this content as quickly as possible so we can start to review and do test preparation. Okay, so acids, bases. Really, there are three theories. We're going to talk about two of them. The first one that we start to talk about is the Bronsted-Lowry model, and this is going to be SL and HL students will need to know this one. The idea is that acids are proton donors, meaning when they get into a solution, they add in this H+. You'll see this as H+ or H3O+, so just water with an extra hydrogen. These are synonymous. This is hydronium. You're going to see both of these. They're interchangeable. They mean the same thing. The reason why you'll see this is because the H+ will actually go on to one of the lone pairs in the oxygen group very readily, and then that will create the H3O+ that you see. And then next up, bases are proton acceptors. A very common proton acceptor that we're going to see is hydroxide, OH-, because what you'll end up with then is if you have this hydrogen meeting up with a hydroxide, you get water. So a very common acid-base reaction is going to be acid plus base makes some sort of salt and water. And we're going to get into all this for sure tomorrow on Monday, but it's going to be a very, very common reaction. You can help use that idea to guide you through the problems. Okay, so remember, Bronsted-Lowry acid is a proton donor, and Bronsted-Lowry base is a proton acceptor. So this is a good example of an acid-base reaction. What we can do here is, well, first off, you should be seeing the equilibrium arrows. So this is not a permanent state. This is a temporary state that's going to be happening. What I'm seeing here is I start off with H2O, and then that H2O ends up becoming an OH-. So in the process of this reaction, it lost an H+, or it donated an H+. So it gave this H group right here, this hydrogen group, onto the lone pair of the nitrogen of NH3. So that makes this the acid, and since the NH3, my ammonia, actually gained that hydrogen, it accepted that proton, that hydrogen. That makes this the base. The reason why we keep calling this a proton is because when you have hydrogen plus, there's one proton and no electrons. And hydrogen rarely has a neutron in there, so it is really just a proton floating through solution, but we just call it H+. One thing I do want to talk about really quickly while I'm here on this slide is you can have something that works as, if you ever have a compound or a molecule that acts as both an acid or a base. Oops, base. This is called, it is called amphoteric. So this would be something like HSO4 minus, where since it does have this negative charge, it can accept a hydrogen and become H2SO4. So in that case, it's acting as a base, or it can lose that hydrogen that it has and become SO4 2 minus, where now since it donated that hydrogen, now it's acting as an acid. So this species, this HSO4 minus, we would call amphoteric. It is an amphoteric species. When you have something acting as an acid, there's something called a conjugate pair. So right here we see the same pattern. I have HCO3 minus, and this hydrogen ends up joining onto the lone pair of the oxygen right there, and it becomes what we call a conjugate base. What that means is if I took this out, this CO3 2 minus, if I took that out of solution and put it into water, just plain water with nothing else in there, it would start to act as a base and become its conjugate acid pair. So this is something that we're going to work on more in class one-on-one because it's easier for me to explain and show you what's happening. So basically an acid turns to a conjugate base after it's given up that electron, and then you can see this base turns into a conjugate acid. Because now that H3O plus can donate a hydrogen. It's just a way to describe what after an acid is donated, what it is. So they're the same species, there's only ever going to be a difference of a hydrogen or somewhere. The other one, this is HL only. The Lewis model, it's an electron pair acceptor, an acid would be, and a base would be an electron pair donor. So this is when we're going to start to keep our eyes out for nitrogens with a lone pair that it can donate to something else and create a bond. An acid would just be an electron pair acceptor. I'm going to spend basically our first HL lesson on this so that we can identify Lewis acids and Lewis bases. But I just wanted you to be on the lookout for this idea. I just wanted to quick show it to you. Okay, so how do we measure how acidic or basic a compound is? We measure it with pH, and I'm sure a lot of us have seen this before. pH is a number that tells us the hydrogen or the hydronium ion concentration, and pOH is the number that donates the hydroxide ion concentration. So pH plus pOH equals 14, and this is just because the dissociation of water ends up being 10 to the negative 4. I'm going to really dive into the deep part of this on Monday. Right now, just accept the fact that pH plus pOH is 14, and then we'll talk about why on Monday this happens. So it's a scale from 1 to 14. This isn't exactly true. We can get negative pHs, and this just means it's incredibly acidic. We can get a pH of 0, as you can see. You can see here, but for practical purposes, it's really just 1 to 14. Anything outside of that range is going to be incredibly caustic or alkaline. Alkaline meaning basic, acidic, it'll end up being very acidic. This is going to give us an idea of the concentration of H+, and it's still just the moles per decimeter cubed. So it's just a normal concentration, and our equation to find pH is negative log of the concentration of H+. If I wanted to find pOH, same exact thing, except I would be finding the negative log of the concentration of OH minus. So pH is just telling you to take the negative log of the concentration, and pOH is telling you to take the negative log of the concentration. Whenever you see that P, you need to think negative log, because we'll end up starting to talk about pKa's and Ka's too. So remember, P means negative log. So then if we were just going to find the pH of something, and I know that I have a concentration of 1 times 10 to the negative 7th is my concentration of H+. I'm going to just do negative log of 1 times 10 to the negative 7th. And I end up getting a value of 7. Do not forget your negative part. That's a very common mistake people make, and it's going to give you out a negative value. It's going to be incorrect if you forget to put that on there. So the number of decimal places here is the sig fig that I'm looking for. So since I have 2 sig figs, I need to have 2 decimal places behind it to give the correct answer. And you can see that right there, 7.00. So for logs, significant figures are different. It's all about numbers after the decimal place. Those are the ones that count. It's called the mantissa, but I don't think IB cares about that. And then so let's just look at another one, how to back solve for pH. So if I know my pH is 6.00, so I'm seeing I have 2 sig figs here, because I have 2 numbers after the decimal place. To undo a negative log, first you're going to move the negative over, so you should end up with a negative pH is equal to the log of the concentration of H+. And then you just raise both sides. It becomes an exponent, and you end up getting 10 to the power. So basically, I give these guys base 10, so my concentration of H+ ends up being 10 to the negative pH when I end up back solving this. So if I know my pH is 6.00, I know my concentration of H+ is going to be 10 to the negative 6.00, or scientific notation, 1.02 sig figs, 2 sig figs, times 10 to the negative 6. POH is the same exact problem process. It's just you'd be finding the concentration of OH minus. We can go from pH to POH very easily through this, the pH plus POH equals 14 equation. I'll help you guys out with all of this in class. I just wanted to give you guys a really brief rundown of a little bit of the math and a little bit of the theory coming into this. We'll get into the more details on Monday, and I'll give you guys a lot of work time as well. Have a nice rest of your weekend, and I'll see you soon.